So I know we've talked about the midpoint rule a little bit, but there's kind of a question about like how you just kind of go about doing it. So it really kind of depends. But very generally, if we want to estimate the area under y equal to f of x on the interval from A to B using n rectangles with midpoints to give us the height of the rectangle. Here's how we do it. Here's my very generic function. Here's A, here's B. And I'm going to attempt to write this in the most compact way possible. So really the idea here is that when you're trying to write the general formula like this, before we do a specific example, you really want to focus in on one specific rectangle, the ith rectangle, or whatever you like to call your index, the jth rectangle, the kth rectangle. So somewhere in the middle here, there is the ith rectangle, or the ith interval. I'm going to call it a rectangle, so I'm going to make it a rectangle. And we need to know what we're calling the end points of that rectangle. And this is where I usually like to go back all the way to the left and look at my first rectangle. Here's my first rectangle. For that first rectangle, or subinterval, which I'll make into a rectangle in a second, the left endpoint is A, which is also x sub what? I almost gave it away, x sub 0. And the right endpoint is x sub 1. That's the typical labeling we use. And that's for the first rectangle. So the way I always think about this is the first rectangle has a right endpoint that's x sub 1. The ith rectangle has a right endpoint that's x sub I. And it has a left endpoint that is one index less than that, so it's x sub I minus 1. And then if we want to use the midpoint to then find the height of the function, so that we can find the height of the rectangle, we're going to find the middle of those two numbers. How do you find the middle of any two numbers? Well, let me say it a different way. Yeah, exactly. I see people mouthing it. How do you find the average of two numbers? You add them together and you divide by 2. So that midpoint there, which I might call x sub I bar, that's a notation for average. That's going to be the average of x sub I minus 1 and x sub I. So the sum of them divided by 2. So now I want to add up all the areas of the rectangle. So I can take a draw rectangle. So what we're literally doing is we're taking that point, we're subbing it into the function to get the height of the function, and then we're using that height as the height of a rectangle. I know my picture is not great, but you can kind of see what I'm doing. So the area of the ith rectangle is going to be the base, which is, I should have talked about delta x. We talked about delta x many times, so let me say it again. Delta x is just the width of each subinterval, which is your total width divided by the number of subintervals. So your a sub I is going to be the function evaluated at your x sub I bar times your delta x. That's kind of an easy way of writing it. If you want to make it look more terrible, you can say it's f of x sub I minus 1 plus x sub I over 2, all times b minus a divided by n. Gross. But that's just the ith one. I want all the areas added up. That's where we're going to not write them all out. We're going to use the summation notation to make our lives simpler. Or at least less terrible. So the total area, which is the, I'm not using right endpoints, I'm using midpoints, sorry. I would deal with this as m sub n for the area using n subintervals with midpoints, would be the sum from I equals 1 for the first one all the way to I equals n for the last one, or the nth one, of this same quantity. f of x sub I minus 1 plus x sub I all over 2 times b minus a over m. That is the very generic formula for how we... Am I not sharing my screen over here? Sorry, 1 second. Yeah, I'm not. Apologies, Zoom folks. If I'm not sharing my screen, please let me know. If you're like, he's saying things and writing things but not doing anything, just tell me. You can write things in the chat or you can say words out loud and terrify me. So hopefully you can see what's going on now. Sorry about that. Yeah. So this is the very generic formula. If you just are given some function and it's an interval and asked to approximate the area using some number of rectangles. And then we can actually do it. The problem is doing it is a terrible computation, right? Usually it's like some not fun function and you then have to like do the thing. So let's say we had something like, let's say we had something like, let's do that. Let's say our function is f of x equal to 1 over x, and we want to approximate the area using 4 is such a common choice. Let's do 6, n equal to 6 rectangles. I probably should have said the interval first, but over the interval from, let's make our life not suck, from 1 to 13. 13 feels like a cop-out, James, but fine. I almost feel like I'm making it too easy, but it's still going to be terrible. So, even though we just talked about that nice formula, I don't really use that formula when I do this. Like if I actually have to do this, I really just want to draw a picture and find the midpoints that way. So yeah, I could find my delta x equal to 13 minus 1 over 6, which is 2. And then I could find all my x sub i's, right? My x sub 0 would be 1. My x sub 1 would be 1 plus 2. My x sub 2 would be 1 plus 2 times 2. My x sub 3 would be 1 plus 2 times 3. But really, like, this is kind of annoying to write this all out. And then I'm going to find the midpoints of those. It's much easier just to draw it. Specifically, the x-axis part, I don't really care about the y-axis function part. I just care about kind of what's going on in the x-axis. So there's 1, there's 13. I'm breaking it up into 6 subintervals, which I know are each going to be a width of 2. I try to do it kind of nicely, break it in half, and then break up each of those up into thirds. So there's my subintervals. My x sub 0 is 1, and then you have 3, 5, 7, 9, 11, and 13. No surprises there. And then the midpoints of these are also super easy because I made it super easy. 2, 4, not surprisingly, all the even numbers. So then very generally, if I'm going to write the area using midpoints, I'm going to say M6 for midpoints and 6 subintervals. And then it's going to be just each base, which is 2, times each height, which is going to be f of 2 plus f of 4 plus f of 6 plus f. So it's going to be 2 times f of 2 plus f of 4 plus all the way to f of 6. F of what? F of 12. And if you want to compactify it, compress is probably a better word to use there. You could write it as the sum from I equals 1 to n and 1 to 6. Yeah, because it's 6 subintervals of f of 2i all times 2. And then you could actually calculate it. I don't think you need to do this unless you want to do this, but it's going to be 2 times f of 2, which is 1/2 plus 1/4 plus 1/6 plus 1/8 plus 1/10 plus 1/12. There is a way to do this on a calculator, like to actually use some sigma notation on some like the TI calculators. There is a way to do it. It's usually not worth the time figuring out how to do it, but there is a way to actually do it, like to enter your beginning index value and your end index value, and then the function that you're evaluating each of them at. It's kind of neat, but again, not usually worth your time. Yeah, we might as well. So do I have a calculator on me other than my terrible phone? Let's find out. Did I bring it? Yes, good, cool. So I'm just curious what this actually is. So if we calculate this here, I could just multiply each thing by 2 and say I've got 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. And we get, that's much too nice to be real. I can't, that's, oh, I guess it could be, yeah. Sure. We get 2.45. You might want to check that. Yeah. Where did, sure. So I really looked at this and just said, this is for my I equals 1. It's for my I equals 2, all the way to this is to my I equals 6. So I just noticed that each of my inputs was exactly twice what the index was. But really, okay, so if I wanted to be more kind of specific about it, what I really would have done is said, okay, my x sub I is, well, x sub 1 is 1, x sub 2, I know I wrote that up. I don't do the same work again, James. Just say that we know that x sub 1 is 1 plus 2, x sub 2 is 1 plus 2 times 2, x sub 3 is 1 plus 2 times 3. So x sub I is going to be 1 plus 2 times I. And then I could take the average of the x sub I and x sub I minus 1 and say that x sub I minus 1 plus x sub I all divided by 2 is going to be 1 plus 2 times I minus 1 plus 1 plus 2 times I all divided by 2. And then if I simplify this, I get 1 plus 2I minus 2 plus 1 plus 2I all divided by 2. The negative 2 cancels with the 1 and the 1, and I get 4I over 2, which is 2I. But you shouldn't do it that way. You should look at the numbers and be like, oh, 2, 4, 6, 8, 10, 12. I can see that that's always just twice the thing I'm putting. So there's an easy way to get there sometimes, and there's also the more algorithmic way of getting there, which will always work, but there's way too much work usually, other than kind of just trying to see it. Oh yeah, and so then what I wanted to actually point out here is that I wanted to compare this to the actual value. So I'm going to start talking about integration, though, even though we haven't kind of really gotten there. But I will point out that the way you can actually calculate the value under f of x equal to 1 over x from 1 to 13 would be to calculate the definite integral from 1 to 13 of 1 over x. And I'm going to start abusing the fundamental theorem of calculus, even though we haven't talked about it yet, just to kind of show you that things are decent approximations. So if we were to calculate this, it would be the natural log of the absolute value of x, the antiderivative of 1 over x, which again, I know we'll come back to this, I promise. Evaluated from 1 to 13. That's going to be the natural log of 13 minus the natural log of 1. Notice I dropped the absolute value there because the absolute value of 13 is 13 and the absolute value of 1 is 1. The natural log of 1 is always 0. So you end up just getting the natural log of 13, which I'm hoping is close to 2.45. And it's 2.56. That's close enough. So yeah, a pretty good approximation using 6 subintervals for this integral. So that's kind of how I would approach the midpoint rule. You can certainly be very kind of calculation based if you want to, but you can also kind of just try to look and see what the midpoints are to find a formula for them. Yeah. So this thing right here, what I did was an application of the fundamental theorem of calculus. It's actually the fundamental theorem of calculus part 2, also known as the evaluation theorem, which is where you find the antiderivative of the function, and then you plug in the top limit of integration, you subtract and plug in the bottom limit of integration. I will also say, since I've kind of opened the box, it's kind of like in Law and Order when they say you can't unring the bell, right? I've said the thing, now it's there, out there in the world. This is the reason why we kind of also use this notation for the antiderivative, because there's this very close relationship between the integral of a function and the area under that function and the antiderivative of that function, and that we use the antiderivative of the function to help us calculate the area under the function. Yeah. No. So this really has nothing to do with the fact that I was talking about the midpoint rule here. I could have approximated this area using right endpoints or left endpoints or any point in between and still gotten an approximation that was relatively close to the actual area. But the actual area here, the answer to this area under the curve question, the real true answer that everyone should say is the natural log of 13. Yes, it's approximately 2.56, but in math classes, we don't usually prefer approximations, right? Unless someone specifically says, give me the decimal approximation for this thing, you should be leaving your answer as natural log of 13 or e to the third power or sine of 5, right? Don't give decimal approximations unless asked for. Cool. All right. So, oh yeah, I put those things over there. All right. Just 1 second here. Just 1 moment. Yeah. Okay. Sure. So let's talk about some properties of definite integrals. Right, that's what you were going. That's what the question kind of was. Yeah. So properties of definite integrals. Really wish they would fix this desk. I feel like I'm hunched over here. Sue. No, I'm just kidding. I wouldn't sue. So yeah. Kind of don't want to talk about that. So let's talk about some interesting properties. Let's look at this example. The integral from 0 to 1 of x squared minus 1. So graphically, I want to point out that the function y equals x squared minus 1 on that interval looks like this. It's a parabola that opens upwards and it's shifted down by 1. So if x was 0, I get the point 0, negative 1. And if x is 1, I get the point 1 minus 1 is 0. And it looks kind of like this. And yes, it would continue on that way and continue on that way. But I really only care about this part here. And so I've been saying a lot of how the definite integral is an expression for the area under the curve. Well, I kind of have to be a little bit more generic about it. Really, it's the net area that's under the curve and above the x-axis. So here, if we were to calculate this definite integral, we'd actually end up getting a negative answer. So we have to be a little bit careful when someone asks for how much area is enclosed by like this curve in the x-axis versus what's the definite integral of this function. The definite integral is definitely negative. We always think of area as being positive. I really don't want to do this the long way. We could. What if I just showed you instead of doing it? We can do it if you want, but I'm just going to show you the work over here, and we can pretend like I did it. Let me just show you what we got here. So, by the way, I'll point out these are not my notes. These are Grant's notes. If you're ever looking for resources about how a thing might be done, in fact, let's just go over there for a second. So yeah, Grant's my good buddy all the time. So let's point out, if you're looking for more resources, that's Grant, by the way. Wonderful person. Excellent at math. And you click on the 17B new book, there are lots and lots and lots and lots of good things to look at. And there's lots and lots and lots of videos as well. So if you're looking for more instruction or more just things written down that you can look at, great place to look. So I do believe I've linked it from Canvas. I'm pretty sure I fixed the link because I know it was broken before. But yeah, let's find out while we're here. Let's see. Do I have a cursor somewhere? There we go. Co-17B. There we go. Let's see. Is it linked in here? I don't see it. Do I not have useful links up here? Terrible. Oh, there we go. Sorry, I missed it. Grant 17B website. Let's see if it works. Success. So yeah, it's in Canvas. All right, so anyway, back to this. This area is below the x-axis. So we could do this the terrible long way, which we're not going to do, but let's just talk through it. So here we'd find delta x. It'd be b minus a over n, which is 1 minus 0 over n, which is 1 over n. Our x sub I, you can memorize this formula for x sub I if you want to. I've done it so many times I finally memorized it, but like really almost every time I would be like, okay, x sub 0 is 0. X sub 1 is 0 plus 1 over n. X sub 2 is 0 plus 2 over n. X sub 3 is 0. Oh, I see the pattern. It's x sub I equals 0 plus I over n. Or x sub I equals I over n. But the very kind of general formula for the x sub I, the right endpoint of the ith subinterval is just a plus I times delta x. You're starting at a, and then you're adding however many delta x's you need to get to the ith right endpoint. Okay. So then we rewrite our area under the curve, or net area under the curve above the x-axis, using the limit definition. This one's not too terrible. It's the limit as n goes to infinity of the sum from I equals 1 to n of just, right, there's your area of your rectangle. It's your height times your width, f of x sub I times delta x. And then our x sub I is I over n. Our delta x is 1 over n. We plug I over n into the function x squared minus 1. We get I over n squared minus 1. We distribute the 1 over n. We get I squared over n cubed minus 1 over n. We break it apart. We pull out the constants. So we have a 1 over n cubed times the sum of I squared minus a 1 over n times the sum of 1. We saw last time, or maybe the time before, that the sum of 1 is just n, and the sum of I squared from I equals 1 to n is this lovely formula, n times n plus 1 times 2n plus 1 over 6. Grant was nicer than I would have been. He actually multiplied out the top. I would have just said I have 2n cubed plus some lesser terms over 6n cubed, and said the limit of that was 2 over 6, because you don't really need to worry about whatever the lesser powers of n's coefficients are. And then this just simplifies to 1. So then we get 2 over 6 minus 1, which is 1/3 minus 1, which is negative 2/3. So back to the point, that region, since it's under the x-axis, its definite integral ends up being negative. We would still say that there's an area of 2/3 square units, whatever your units are, in that region, but the actual definite integral has a negative value. Let's see what Grant's, how does Grant like to say this? Yeah, the actual area is positive 2/3, but the definite integral will come out negative because the function is negative. Cool. Questions about that idea? So again, the limit calculation, terrible. But the idea here that for regions where the function's under the x-axis, the integral, the definite integral comes out negative, I think should be relatively clear, right? We're saying, oh yeah, and it's really happening because, I don't know. No, I don't want to say that actually. It's happening because it happens. That's why it happens, because it happens. Because the answer is negative. Questions about this particular thing? Oh, I know. Yeah, I was thinking of something else. That's good. So I would just point that is negative. So just to kind of go back for a second to the, sorry, let me minimize this, which I might not be able to do here. I wish the screen was working. Sorry, one sec, come back. Why do you not want to be nice to me? Can I not minimize you from here? Okay, fine. Sorry, I'm like, okay, go away. Thank you. Okay, so I would just point out, if you were going to do this using the evaluation theorem, which again, we're almost on the precipice of getting to, you could write this as the antiderivative of x squared minus 1, which is x cubed over 3 minus x, evaluated from 0 to 1. We end up getting 1 cubed over 3 minus 1 minus 0 cubed over 3 minus 0. Yes, I know that 0 cubed over 3 minus 0 is going to be 0, but I just want to write it out to encourage you to be careful about plugging in 0. You don't always get 0 when you plug in 0, so just make sure that you're thinking about, if you're thinking you get 0 when you plug in 0, then do a mental double check and be like, okay, if I plug in 0 to all those things, do I actually get 0? Okay, great, move on. Yes, you should just normally write this as like 1/3 minus 1 and then simplify it as negative 2/3. Okay, so one of the properties is area under the curve, under the x-axis, gets counted as negative in the definite integral. What about some other fun properties here? I actually wanted that. I was trying to move that over to me. Sorry. I want to make sure I say the right things. Oh my gosh. What's the problem? Okay, come back. Come back to me. Thank you. All right, cool. So, yes. What about something like this? I'm going to change it up a little bit. Sure. How about the, no, let's not change it. The area under the net area under the curve. I don't want to say all those words every time. I'm going to say area under the curve. You're going to know I mean the net area under the curve that's above the x-axis. Probably. I'll probably still say it because, yeah. Well, let's say I want to find the net area under the curve above the x-axis for the integral for the function x cubed on the interval from -2 to +2. Drawing graphs is your friend. You want to draw the graphs to see what the thing looks like. Sometimes that's going to really, sometimes it's going to make the problem possible where it would otherwise be impossible. Sometimes it's going to make it easier. Like this problem here, especially if I had to do this one the long way with a limit definition, I wouldn't want to. And I don't have to. Because if I draw this, look what happens. This is never my favorite function to draw. Well, the problem I have with drawing this is it's there should be some symmetry, and I'm bad at drawing this symmetry. That's pretty good, I guess. So I'm going from -2 to +2. And here's what I want to point out, which you can probably already start to see. This area here, whoa, that's where 2 is, sure. This area here is some positive number. And this area over here is some negative number, but it's the corresponding same or opposite, I guess, really, right? That number there is the opposite of that number there. And when you add those areas together, what are you going to get? If you add the same negative number to the same positive number, 0. And that's going to be true for any odd function if the limits of integration are negative number to same corresponding positive number. I should just say the opposite numbers. If the limits of integration are opposite numbers, negative a and positive a. So it is true, the integral from negative a to a of f of x dx is equal to 0 if f of x is an odd function. Later on, if we get into talking about improper integrals, there's a little caveat here that we have to add in. But for now, as long as that function is defined on the interval, it's going to be 0. So this actually brings up something interesting. You might see on your first test or whatever quiz, some quiz, you might see something that looks completely ridiculous. Like, say, the integral from -2 to 2 of x squared times tangent of x divided by x cubed plus 17. Yeah, we're safe there. We're safe there. Yeah. Which to x cubed, James? We are not safe there. X to the 4th. Sorry about that. Okay. So that looks ridiculous. And once we start learning how to use the fundamental theorem of calculus, that does not look like a function that I know how to anti-differentiate. Because it isn't. Because it's probably impossible to anti-differentiate, to be perfectly frank. There's a hint here. And the hint is that the limits of integration are opposite values. Seeing that -2 and that 2 makes you think, oh, they probably wrote something terrible because it's probably an odd function. But at least if I were grading your work, you can't just say this equals 0 and just state that the function is odd. You have to show that the function is odd. So we need to show that f of x equal to that integrand x squared times tangent of x, all divided by x to the 4th plus 17, is odd. How do you show a function is odd? Good question. So here's the way you should think about it. If I plug in 2, I get 8. If I plug in -2, I get -8 for this previous example. So what we're looking for is that when you plug in the negative of your original x value, you get the negative of your original y value. That's to show something is odd. Odd function. If you want to show something's even, you just want f of -x to equal f of x. You want the same y value for the opposite x values, like y equals x squared. So here, we're going to start with, I would always start with f of -x. Just sub it in for every x value, so you get -x squared times tangent of -x, all divided by -x to the 4th plus 17. If you need clarification, I'm happy to clarify. If it's hard to read something, I know my writing's not great. Okay, or not. Speak up if you have something though. So -x squared is x squared. Ooh, tangent of -x. Is tangent even or odd? Good question. Every trig function on its own, sine of x, cosine of x, secant of x, tangent of x, cosecant of x, cotangent of x, are all either even or odd. I should say each one of them is either even or odd, right? The reason I say that is because not every function is even or odd. There's plenty of functions that don't have any symmetry. Even symmetry being you get the same thing if you reflect on the y-axis. Odd symmetry being if you rotate the thing 180 degrees, it looks the same as it did. You could also think of it as reflecting in both the y-axis and the x-axis and looking the same. Lots of functions don't have that symmetry. Think of e to the x. It has no symmetry. Did I say the thing about your right hand being e to the x? My right hand is not great for this because there's lots of lines on it. But if you look at your right hand, that line curve there looks kind of like e to the x. That curve there, which is really just, worn out there, is natural log of x. So if you're looking for those functions, there they are. But e to the x and natural log of x both don't have any symmetry. They're not even, they're not odd. Yeah. So lots of functions, most functions are not even and not odd. But the trig functions are. And tangent, not tangent odd. It's kind of weird to think about. So if you think about tangent, I don't want to draw all of it, but just the middle portion of it from negative pi over 2 to pi over 2, I kind of hate to say this, but kind of looks like x cubed. Not really, because x cubed doesn't have vertical asymptotes. But it kind of looks like that. And then if you were to rotate that 180 degrees, it looks the same. And then if you draw the rest of it, that part rotates over to that part over there, and that part over there rotates to that part over there. So yeah, this really does rotate fully. It's kind of neat. In fact, if I was smart about it, I can be smart about it, you can see that by just literally rotating the paper. Oh, it looks the same. It's much easier than trying to show even symmetry because you can't just flip the paper unless it's like kind of translucent. Anyway, tangent's odd, kind of great. So that means that if tangent is an odd function, that means that tangent of negative x is equal to negative tangent of x. So I can write this as negative tangent of x. I switched colors, sorry about that. Negative x to the fourth is just x to the fourth plus 17. And then the negative comes out in front, and we do in fact get negative x squared times tangent of x over x to the fourth plus 17. So that is equal to negative of the original function. So yes, f of x is odd, which means this is equal to 0 because the integrand is odd. Or is an odd function, is I suppose what I should technically say here. So again, I'll say, if you see something like this on an exam, where it's negative 5 to 5 of something terrible, or negative 17, right? Negative number to the same positive number of something terrible, it's a hint that it's probably an odd function. And you're probably going to get just 0. Okay. Let's look at a few other things that come up that might feel somewhat counterintuitive. Like, say, for example, I want to find the area under the curve, under the absolute value function, 2x minus 4 from x equals 0 to x equals, 5 is fine. 5 is fine. Sure, 5 is fine. And I would certainly mention that once we officially have learned the fundamental theorem of calculus, evaluation theorem, you can do this that way. You can certainly break this apart as a piecewise function into 2 pieces, and then anti-differentiate each piece over the appropriate interval, and then get the right answer. Or you can do it the easier way. The easier way being graph it. So that's an absolute value function. I know it has kind of a V shape. Whenever I'm graphing an absolute value function, I'm looking for the bottom of the V, which is actually called the vertex. So it's kind of the only other thing I can think of that has a vertex other than a parabola. But absolute value functions do have a vertex. And the vertex is going to be when 2x minus 4 is equal to 0. So x is going to equal 2. So there's the bottom of my V, which when x is 2, I do get 4 minus 4, which is 0. And then it's just going to look like straight lines kind of going like that. So I'm going to find some points. Like when I plug in 0 for x, I'm going to get positive 4 for y. And when I plug in 5 for x, I get 10 minus 4, which is positive 6 for y. And if I'm trying to find the area under that curve from 0 to 5, those are triangles. And I know how to find the area of triangles using regular geometry formulas. And that's what we should do. So I've got that area plus that area. This is going to equal the area of this triangle, which is 1/2 the base, which is 2, times the height, which is 4, plus the area of this triangle, which is 1/2 times the base, which is 3, times the height, which is 6. And then we simplify that and we get 4 plus 9, which is 13. And even if you could do it a different way, you really shouldn't. This, I mean, not that you shouldn't like know how to do it another way if you want to, but this is the easiest way to do it. And I'm all about doing it the easiest way because there's going to be lots of questions on your exam and you want to do it, get through them as quickly as possible. Yeah, let's do this. So I should always say questions, comments, concerns, thoughts. I will say you couldn't do this if you were like asked to find the area under the absolute value of something that wasn't linear. So if you had like the absolute value of 9 minus x squared, for example, from something terrible like 0 to 7 of the absolute value of 9 minus x squared, then you would have to break this up into two pieces because the absolute value of 9 minus x squared looks like 9 minus x squared, which is a downward opening parabola shifted up by 9. We have x-intercepts at plus or minus 3. And then instead of continuing downward underneath the x-axis where it would be negative, you take those parts and you flip them across the x-axis to make them positive. So instead of getting all of this down here, you say, oh, it's really going to go this way instead. Which is terrible because it just is. And then you would say, I want to go from 0 to 7. So I know that doesn't look like it's 7, but we'll pretend it is. So you'd say, there's my 0 to 3 and 0 to 7. So you have to break this up as the integral from 0 to 3 of 9 minus x squared plus the integral from 3 to 7 of the negative of 9 minus x squared. That's how you deal with a more complicated absolute value thing. But you probably won't see that. So let's look at something you will probably see. Time 10 minutes. 10 minutes. Let's say you want to find this. The integral from, yeah, let's do that. Negative 6 to 0 of the square root of 36 minus x squared. This function can be anti-differentiated. We will not learn how to do it. There's a method of integration called trig substitution that's required to do this. We don't learn that in this class. And we don't need to learn that to be able to do this integral. Because if we graph it, this function might look familiar to you. It might not. It's totally fine if it doesn't. But you might recognize that this is the, well, it's part of a what? Part of a circle. It's the top half of the circle. What if it was y equal to negative square root of 36 minus x squared? Bottom half of the circle. So this is the top half. I'm going to graph it. Got a radius of 6. I don't know why I'm making marks here. That's really pointless, James. They started doing it, so now I can't stop. Wow, it's not the best half of a circle I've ever drawn, but you get the point. So my points here are negative 6, 0, 6, 0, and 0, 6, which you can certainly see if you plugged in any of those points, right? You plug in 6 for x, you get 0 for y. Plug in negative 6 for x, you get 0 for y. Plug in the 0 for x, you get 6 for y. And if that isn't obviously a circle to you, the way you can make it more obvious is by squaring both sides and then bringing the, sorry, that's a, whoops, the y squared equal to 36 minus x squared, and then adding x squared to both sides. You see, oh, that, it looks like your usual typical equation of a circle centered at the origin with the radius of the square root of 36, which is 6. So then we have to find the area. But we can just use the formula for the area of a circle. What fraction of the circle do I have? Sorry, I'm very deaf. 1 how much? 1/4, right? Because it's from negative 6 to 0. So it's a really good idea to say there's negative 6, there's x equals 0, and to just shade in the parts that we have. So in this case, the area, the answer would be 1/4 times the area of the circle, which is pi times your radius squared, which ends up being 9 pi. On the other hand, if they gave you the integral from negative 6 to positive 6 of the square root of 36 minus x squared, you would end up getting 18 pi because it would be half the circle instead of a quarter of the circle. Those are the only kinds of questions you can really ask about this kind of function. If your limits of integration are anything other than negative radius to 0 or negative radius to positive radius or 0 to positive radius, if it's anything else, it's not doable. But it won't be anything else because, okay, fine. We won't probably see this, but super annoying when we do this. sometimes people ask like, what's the interval from 0 to 3 of this thing? And then you do some like crazy trick stuff where you're like, oh, from 0 to 3, I'm gonna like say it's gonna be, or maybe from 3 to 6 is better. Like if I was doing from 3 to 6, it's all that. And then I like have to say it's like this section, this like portion of the circle, this like pie slice of the circle minus this triangle, and like this angle ends up being something convenient, but it's super dumb. We won't talk about it unless we have to. But if you end up seeing like something like this, like the integral from 0 to 1, I don't love that, James. The integral from like 1/2 to 1 of the square root of 1 minus x squared, where it's not a full quarter of the circle or a full half of the circle, where it's like some weird, right? This is not an eighth of the circle. It's not half of a quarter, right? Because that portion isn't as big as that portion. Come tell me, and then we'll talk about the terrible trigonometry you have to do it. Okay, what's next on my agenda here? Sure, yeah, I can talk about that. Okay. Yeah. The 1/2 one? Oh, do you want me to talk about it? Okay. Now I have to remember how to do it. So, mildly surprised that she did that. So again, pictures are great. Draw a better one this time. So this is a circle whose radius is, or I should say the top half of a circle whose radius is 1. Try to draw it reasonably well. Fail, it's okay. Doesn't have to be perfect. And then we're looking at 1/2 here. And we're trying to find the area under the curve between x equals 1/2 and x equals 1. So we're trying to find this area here. And so what I'm going to do is I'm going to look at this here. So formula you probably don't remember, but you might, is that, well, actually, let's talk about what we do remember. So the area of a circle is pi times the radius squared. And there's this whole kind of thing. In fact, if you're interested, you should go look at, oh, I remember the tau. What is this guy's thing? The tau something. Something about how tau is better, how 2 times pi is the better constant. Because it's like a full circle as opposed to half a circle when we talk about radians. It's called like the tau, the Taoism. I don't know, whatever. It's cool. It's interesting. But I would encourage you to think of this just for a second as 1/2 times 2 pi times r squared. Or in other words, the area of the circle is 1/2 times the angle we go around times the radius squared. And that's true no matter what angle you subtend, I guess is the technical correct word. So if I wanted to find, say, like the area of this sector of a circle, whose radius is r and angle is theta, the area of that is going to be 1/2 times the angle that we draw out times r squared. That's the area of a sector formula. Cool. So we could find the area of this sector if only we knew that angle. Well, trigonometry time. That triangle there, that right triangle there, has a base of 1/2 and a hypotenuse of 1. And we can certainly find the other side. Do I need to find the other side? You just have to find theta. Or I guess I could say, I don't need to find the other side here. I'm going to say that, so let's say I have the adjacent, I have the hypotenuse. So I could say that cosine of my angle is equal to 1/2 divided by 1, which is just 1/2. Okay. Trig knowledge time. What angle can we take? What nice angle that we all might have seen at one point in our lives can we take cosine of and get 1/2? How much? Oh, that's a good guess. But cosine of 45 degrees is √2/2. 60, let's see. Is 60 the right one? I believe it is. Cosine of 60 is the smaller value. It's 1/2. But in calculus, degrees are shunned and we use radians. So the angle here should be pi/3. That's our angle. That means the area of this sector here, all in blue, the area of that's going to be 1/2 times your angle times your radius, which is 1 squared. So the area of the blue part is pi over 2. And then I'm going to subtract off the area of the triangle to get the area. Oh, that's how I need to find the height. I know I need to find the height to get the area of the red part there. So the area of the sector is pi over 2. The area of the triangle is going to be 1/2 the base, which is 1/2, times the height, which, okay, Pythagorean theorem. 1/2 squared plus y squared equals 1 squared. So y squared equals 1 minus 1/4. So y is equal to the square root of 3 divided by 2. Which I should have known, because if cosine is equal to 1/2, then sine should definitely be equal to the square root of 3 over 2. Oh well. So then the area of the triangle is that. So it's 1 times 1 times root 3 over 2 times 2 times 2, which is 8. Feels kind of small, but I guess that's right. And then we subtract them to get that the area of the integral is equal to the area of the sector, which is pi over 2, times the area of the, I missed one thing, sorry. The area of the sector is not pi over 2. It's 1/2 times, what? You guys let me get away with that. What was my angle supposed to be? Pi over 3, oh my goodness. Like, this seems way wrong. Okay, that should be pi over 6. Oh my goodness. Okay, that's much better. Okay, so it should be pi over 6 minus root 3 over 8, which I guess you could get a common denominator and say it's 8 pi minus 6 root 3 all over 48. Gross, but doable. But really only doable if you're exactly halfway between the origin and the endpoint of the circle. So yes, there is one other weird example you can do without knowing how to do the antiderivative of that function. Cool. See you all on Monday.